Hi, my name is Samir Desai, and in this video, I'm going to teach you how to rank the reactivity of weak acids or bases based on Ka or Kb.
We can measure the strength of an acid quantitatively through the acid dissociation constant, Ka. As we learned in previous videos, Ka is the ratio of the acid ionization products to the reactants. An acid that is more likely to dissociate, meaning an increase in the concentration of the ionized products, will lead to a larger numerator and a larger acid dissociation constant. When we have an acid dissociating in water, the Ka can range from 1 times 10 to the negative 14th to 1. A Ka of 1 times 10 to the negative 14th is a very, very small number, and a small Ka indicates a weak acid. A weak acid will dissociate less, so we'd expect it to be less reactive. The opposite trend would follow suit when the Ka is larger. As the Ka approaches a value of 1, the larger Ka tells us that we have a strong acid. Since the acid would be expected to dissociate more, it would be more reactive. And just like we have a way to measure the dissociation of an acid, we can also measure the dissociation of a base. Very similarly, we can calculate the strength of a base, Kb, through the ratio of the base ionization products over the reactants. And just like Ka can have a range of 1 times 10 to the negative 14th to 1, Kb also shares this range. The trend of Ka and Kb are also identical. A Kb of 1 times 10 to the negative 14th is a small number, and a small Kb indicates a weak base. A weak base will dissociate less, so we'd expect it to be less reactive. Again, the opposite trend holds true when Kb is larger. As the Kb approaches a value of 1, the larger Ka tells us that we have a strong base. Since the base would be expected to dissociate more, it would be more reactive. Let's apply this knowledge to the following slide, where we're given acids with their Ka values and asked to rank them in order from most reactive to least reactive. If we recall the trends from before, the most reactive acids will be the ones most likely to dissociate, so the Ka will be the largest, and the least reactive acids will be the least likely to dissociate, so the Ka will be the smallest. So let's start by ranking the Ka from largest to smallest value, so we can identify the acids by decreasing reactivity. The values of Ka are in exponential notation, and the values of Ka are dependent on the magnitude of the exponents. Therefore, a Ka of 1.3 times 10 to the 6th will, by far, be the largest Ka, and hydrochloric acid will be the most reactive. With the remaining 3 acids, 7.5 times 10 to the negative 3rd will be the second largest Ka. Therefore, phosphoric acid is the second most reactive acid. Make sure you don't get tripped up with exponents, because something 10 to the negative 3rd will yield a larger number than 10 to the negative 5th, or 10 to the negative 7th. 8 times 10 to the negative 5th has a value less than the Ka of hydrochloric acid and phosphoric acid, so ascorbic acid belongs third on the list. This means that a Ka of 4.3 times 10 to the negative 7th is the least reactive, resulting in carbonic acid at the bottom of the list. Since the base dissociation constant works identically to the acid dissociation constant, you should now feel comfortable ranking the reactivity of weak acids or bases based on Ka or Kb. Make sure to follow up with practice questions to solidify this concept.